Right. Welcome Tiffany Duneau, who's going to talk about solving logical puzzles in DisCoCirc. So it's all yours, Tiffany.
Thank you. Yeah, I'd like to thank everyone for the organisers for having invited me to give this talk. So I'm going to be talking about the problem of understanding and solving text represented logical puzzles. So in particular, how we can give enough formal and logical structure to our words and our encoding in order to be able to solve the puzzle just via how we're constructing the, just in how we get the meaning of the puzzle text. So as a kind of overview of the talk, I'm going to just kind of briefly describe the formalism that we're going to be using. So that's the DisCoCirc, which we've kind of just seen, I think, with Bob and Vincent's talk just now. And a specific example of a logical puzzle and how we can solve that. And then I'll just finish with some considerations. Things. So starting from the start, in order to understand logical puzzles, we need to be able to understand sentences. As kind of we've just seen, we're taking, well, we have wires, and these are going to be our characters in our text, and then sentences are going to kind of take the form of a box that has kind of output wires. So we can kind of see this sentence as something that updates the meaning of the input characters. So we kind of plug Alice in and get out cat-loving Alice from our sentence. So viewing things in this way then means that it's very easy to compose sentences together to get the meaning of the text. So in this case, we just plug wires together, making sure we respect the wire types. So we can get a kind of overall diagram that represents the whole text. And it's kind of got the same form as the individual sentences. See that there's still some input wires and some output wires, and there's stuff happening in the middle, which is just the kind of things that are updating the meaning. So if we want to actually know what the overall meaning of this sentence is, because at the moment it's a kind of it's a function or a kind of morphism, then we have to plug in some kind of input state. So maybe a kind of prior knowledge about Alice, the cat, and the dog. So we can kind of get an overall meaning state for the whole thing. So we're just drawing these as triangles. Well, this doesn't mean much yet because we don't know what the kind of boxes and wires in our diagram mean. So for this talk, I'm going to be taking the wires to be sets and the boxes to be relations. So you could also pick basically anything that works or that makes a monoidal category. So another common one is picking vector spaces and linear maps. Nicely with the vector kind of space model meaning. But so the kind of everything I'm going to present here could be ported over there, but I'm just using relations as that kind of gives a easier example to follow. So once we've kind of got our diagrams, what can we do with them? So the main thing to keep in mind is that we can move things around as long as we respect the connections. We can also cross wires over if we need to, just because, well, even if Alice has been introduced on one side of the diagram, she might end up having to connect to the dog, which is kind of on the other side. And so we just need to cross a wire there. If we need to. So we can put things next to each other too. And this is going to be represented by taking a Cartesian product of the sort of either the kind of elements of the set that are flowing through the wires, or kind of the relations themselves, which just apply each relation to the relevant part of the product. Another important thing we'll need is kind of the idea of sums. So we're viewing these as kind of a stack of diagrams. So the inputs and outputs are all going to be fixed, must be the same on each layer, but something different can happen in the middle. So encapsulates the idea of maybe doing something conditionally, or having kind of a union of different relations that we might want to kind of have acting on our diagram. So then DisCoCirc is kind of helping us give details about and looking into how exactly the sentence boxes are built up. So without, rather than going into a lot of detail about the grammar again here, I'm just kind of going to gloss over that and consider building sentences up directly. So we'll still have building blocks, but we won't be going via the grammar in this presentation. Building blocks are these copy spiders or Frobenius dots, as you may have encountered before. Basically, for our purposes, they're acting as a kind of intersection. So there are a stack of diagrams where on each layer, we're ensuring that every wire has the same element value. So all these wires are the same type going in. Yeah, so the structure we'll need is something that allows us to convert between having objects next to each other and kind of merge them into a single wire. So this kind of making use of the sum. Then we'll also include some structures which aren't actually part of officially part of the diagrammatic framework that we're using, but we're kind of putting in as a shorthand analysis that is just kind of copying the input state, so doing it twice. And then we'll also include negation, which in this case it's kind of returning a the set theoretic complement of whatever input subset we're giving it relative to the wire type. So obviously that's not actually a relation, because if we wanted a single relation to do this, it wouldn't work. In each element versus if we had the full subset, we want to return nothing. So this is for if we want to implement negation, we just need to think carefully about how exactly we're doing it so that it works okay for the person who's going to use it for. So the next things we'll need is ways to split up our wires. So if we have an X, but we only care about the red X's and kind of don't want to talk about the green in a given sentence, we need a way to split them up. So we'll do this kind of based on a partition of the set X, where we've kind of labeled the set X in green just to highlight that we're changing the wire type as well with this morphism. So on a specific element, it will then send that element to the wire it kind of belongs to, and then fill all the other wires with a kind of dummy summation moduloid kind of plus blob element. So that's just there to make sure that if we kind of view this as a single layer of diagram, that that layer doesn't disappear because there's nothing. If we're kind of taking the Cartesian product of nothing with something, that kind of gives us nothing. So we still want the X to keep going, which is why we're adding those in. But they're kind of, well, they get removed, well, when they're kind of merging back together using the plus monoid at the bottom. And the black blobs there are just kind of encoding and decoding morphisms to change between the wire types. So those are all the ingredients we'll need. Here's a puzzle, and we're now going to just kind of go through it and see how we can, well, first find what it means, and then solve it kind of at the same time. So there's kind of three sections that kind of serve different purposes in how we're encoding things. So the first is just setting up properties. So here we're just using our psi morphism to combine azure and cyan Ys into one. So in this case, I've mentioned where the sentences are actually on characters. In this case, the characters are kind of azure and cyan and blue, because we're learning about blue as this is kind of a definition. So they're not always kind of maybe the characters we'd expect, like Alice, or kind of that move and do things. But yeah, so we can combine properties that are mutually exclusive by using the simorphism to kind of put them all into one wire. But if we want to have things, properties that can be held jointly, we'll just kind of put them next to each other using the Cartesian product. So that sets up kind of what our kind of properties mean, but then we might have some correlations in between certain properties. So to set those up, we'll use the trick where we can split up a native into kind of the blue stream and a red stream using our phi morphism. And then from here we can apply the sentence to the blue natives. So in this case, it's just kind of intersecting the honesty wire, which we colored red, with just the single state of lying. And then on the other side, we've also needed to add in a kind of extra projection onto the dummy element for the blue natives, just so we can make sure that the red native kind of stays there and doesn't disappear. And then we just merge everything back together into one wire to finish the thing. And then so the next stage is to introduce the actual kind of characters that we'll be dealing with for the rest of the problem. So in this case, we're introducing 3 natives. So we just kind of copy the native kind of that we'd constructed in the previous part into the 3 copies that we need, and then index them so we can refer to them later. Yeah, so and then another thing we might learn is about uniqueness constraints. So in this case, if each native is a different color, we need a way to ensure that we're not getting any, any duplicate colors. So we do this using this kind of permutator morphism. So this is effectively a big sum over all the possible ways we can assign the colors uniquely to each of the characters involved. Yeah, it looks like that. And so the last part of our problem is just going to be just kind of actually the part where we need to learn about the what the characters are doing and what their kind of relationships are. So in this case, both of these sentences in this stage are of the same form. Somebody says that someone else is something. So we'll kind of construct a kind of sentence schema box that we can just apply. So in this case, we have 2 characters, X and Y, and then a property Z that we're assigning. So in this case, we've got a kind of, in the middle, we can see a control negation operation. So the X's honesty wire is controlling whether we're applying Z to Y or not Z. So that's kind of intuitively what we want. And it's picking this specific encoding that helps us fit in with the rest of the diagram. So putting everything together, we then get a full encoding of our puzzle. So without these states at the top, this would just be a kind of representation of the text as a function on kind of the prior knowledge that we might have. So just putting in this prior knowledge, in this case, we don't actually need any. So we're just using kind of singleton elements that just kind of say which highlight which wire type they're from. But they don't carry any extra information because we just don't need it. And so in kind of simplifying this, you might then be able to see kind of what the meaning actually is of this puzzle. So we just kind of do this step by step. First, we can just combine the psi with psi the singleton elements. So we'll just kind of do that, and that gives us the subsets, well, the sets of kind of allowed values, and then applying the correlations. Here, well, on the kind of initial diagram, I just ignored the projection of the plus bit just to make it easier to read. But when we expand it all out, we can see that there's these 4 terms. And then the diagonal terms here, we can see that they'll cancel out, because here we're projecting onto a dummy element which just kind of isn't included in these top 2, well, in these elements here. And likewise here, we're trying to intersect L with the dummy element, which again won't work. So these 2 terms will just disappear, and we'll be left with the 2 terms we're interested in, which is just doing nothing to the red native and making sure that the blue natives are liars. And so kind of recombining them with psi will just give us what we expect, which is just kind of the native with that initial sentence correlator applied. So then we can just go ahead and do the same with the second correlation. And in this case, we'll get a kind of state which represents a possible native. So it's just a kind of a collection of all the possibilities that they could be. So putting this back onto the rest of the diagram, we can just simplify this one quickly, going through copying it, and then assigning the states that we need, the indexing states. So next we're applying the permutator to the color wires. So I won't show explicitly how we're simplifying that one, just because it's a huge sum and it's not particularly enlightening. So we can just move straight onto the plugging in the the kind of this sentence box that we had into the random places. I'll just note here that in this example, we've kind of had a very straightforward plugging in of this sentence schema, right? Because we know who Xavier and Yvette are. But if we had a sentence that was, say, the red native says Yvette is a Z, we'd have to first figure out who where the red native is. So to do that, we'll use the same kind of correlation trick we used. So we'll just split each native into a red and a non-red stream, and then be able to plug in the sentence in the right place. So this is the kind of last step of the diagrams. Simplifying all of this will give us this kind of final state here, which, as it turns out, is the solution to the problem. So we've kind of just done it directly. If we remember from the start, this was just what the meaning of the whole, these 10 sentences were. So we've just managed to compute the solution at the same time, kind of by using the formal structure of the the DiscoCirc, and also by introducing kind of logical elements to the way we're encoding some of the words. And that's kind of allowed us to calculate the solution as we're going along within the problem. That's quite cool for NLP, but where does the quantum come in, since this is a QNLP talk? It turns out that all these diagrams kind of live in the same they're related to the diagrams that we use to describe quantum circuits. So, for example, the ZX calculus is kind of in the same sort of categorical framework. So we can just kind of convert them fairly straightforwardly into quantum circuits, and then, potentially solve it on a quantum computer, or use other methods like tensor network contraction, for example, to kind of find the solution to our diagrams. To summarize, what we've found, what I've kind of presented as a way to solve the kind of logical puzzles we might find in a Raymond's Mullion book, by simply by looking at the meaning of the kind of the puzzle. But we might wonder whether that can be extended to anything else. And it turns out that this is actually just a method that applies to constraint satisfaction problems in general. because they share the same structure. So we initially set up some properties and then introduce some objects and have some constraints that kind of relate these both together. That's kind of the same structure that we use to when we're going through the puzzle. That's the same steps. So you could apply the same approach here. And then, well, looking towards maybe more real-world problems, reading comprehension is a kind of domain that might that seems that this could work quite well. In particular, because we're leaving open the possibility of having prior knowledge. So that could be introduced just as it plugging in some kind of more sophisticated states to the top of the kind of morphism that affects the sentences in order to get kind of more detail from it. But yeah, thank you for listening. Thank you.
Thanks a lot, Tiffany, for this fascinating talk. Let me just check the Slack channel. I think so far there's no question apart from a comment from Richie saying this is very cool. I agree.
Thank you.
I don't know whether further questions will come up. Maybe just a quick general one. I wondered whether you've thought about ways or whether you have intuitions and ideas how one could make it, say, more generic, as in where the writing down of the diagram isn't already informed so much by your or our understanding of what the puzzle is about, where you could just feed it some text and it just transforms it into a circuit to process and get the answer without having analyzed it by a human, if that makes sense.
Yeah, so if we're looking into kind of more details on how the sentences themselves are constructed, it seems that there's quite some room to kind of, well, looking at the grammar to inform how we're constructing our sentences, kind of on a more word-based level. So if we kind of think of like the difference between when we're talking about things in general, so the kind of azure is a type of blue, that's quite different to saying that cat is green, and that kind of has a grammatical difference as well in how we're kind of in the form of it. So that could inform the kind of different sorts of encodings we're using. So in the kind of setup phase, with picking the kind of the first in the kind of azure is a type of blue form, whereas when we kind of in the last section, it's more of a kind of, we're talking about specific objects, and that gets picked out by kind of adding the in front of something or using a specific name to refer to them. So that's kind of somewhere to look at how to use those cues to inform how we're encoding things.
Okay, thank you. If there are no further questions now, I see somebody's typing. It doesn't quite appear yet. You can always answer and have a discussion on Slack. So maybe, yeah, let's end it here. Thanks a lot again for this very nice talk.